And what economists would like to do is to come out with some sort of way of making a set of assumptions so that we can pretty much guarantee what outcome Smith and Jones would arrive at in a real world marketplace. And that's what we're going to turn our attention to next. Okay, so now what I'm going to do is I'm going to change essentially the assumption that Smith and Jones are just utility seeking. Utility seeking is going to get us an outcome that they trade somewhere into the lens, but I don't really know where. What I'm going to add into that is a standard sort of set of assumptions in economics, which is, first of all, to say, let's imagine that Smith and Jones are rational. Now, rationality is a very complicated concept, meaning different things in different contexts. But in general, sort of at a first glance level, it means that Smith and Jones are going to use all the available information that they have in making their decisions. And remember, we're going to imagine they have perfect information. So they're going to use all of that information as best they can. And if they do, being rational, we should imagine that they're never going to leave any gains from trade unrealized. If it's possible for them to gain further, they trade to a particular point like D, for example, back in the diagram here. So if they trade to D, they're going to get an increase in utility, right? But if you go back to this depiction where I have all these indifference curves up, if they move to point D, they're both better off. But notice that at point D, there is still a lens being created in here. And that lens means they can still trade further and actually both become better off again. So being rational means they would never allow themselves to stop at point D. They would use the information, they would throw out some additional trades that were possible, and they would realize that there's some other trades out there that would actually make both of them even better off than at point D. Okay, so rationality is going to imply that they don't get stuck at point D, that they actually exhaust the gains from trade that are possible in this particular situation. Back to here. And then the next thing we're going to do is to assume that Smith and Jones actually maximize their utility. Now this requires a mathematical expression of this particular problem, and it requires a mathematical exercise where we maximize utility subject to the constraints faced in trading with the other and the terms of trade that might be realized. This is a mathematical exercise that we're not going to do in this class. We're going to work with the outcome of that mathematical exercise to display what the outcome is likely to look like. And that's what I want you to learn just a little bit about and what we're going to go over next. Okay, so as I say, we will not derive this condition. We're only going to present it graphically. And that's why it's going to be a little bit confusing, no doubt, to you, because I can't build it up from first principles. I can't show you, I don't want to show you the mathematical maximization or calculus problem that allows us to get these conditions. I'm just going to show you the outcome or the conditions and then display them on the graph, and we're going to make some sense of it that way. Okay, Pareto optimum. And sometimes, too, we're going to call this Pareto optimal. So either word is acceptable in this context. We want to talk about a Pareto optimal allocation. And that's going to correspond in our Edgeworth box diagram to any point such that there's no trade that's possible that can make both of the traders better off from that point. So another way of describing Pareto optimum allocations is the gains from trade have been exhausted. There's no additional gains that the two can realize through further trade beyond that particular point. Right now, down below is the mathematical condition that's necessary for Pareto optimum to be true. And it's going to be the following here. It is a ratio of marginal utilities between oranges and apples for Smith compared to the ratio of marginal utilities between oranges and apples for Jones. Now, we defined marginal utility, this term up here for oranges or apples earlier on in the slideshow. And we said it's just the additional utility that Smith gets from an additional orange that's added to his consumption bundle. And that's going to vary based on how many oranges he already has in his bundle. And he can calculate his marginal utility of apples as well at each individual consumption level of apples. Well, if we take the ratio of those two, it creates something down here called MRS, and MRS is the marginal rate of substitution. Again, a terminology you don't need to worry too much, just remember that MRS is equal to this ratio here. And even then, what you really need to remember is that the marginal rate of substitution corresponds to the slope of the individual's indifference curve at a point. So let me go back to a diagram here. If I were to look at point C and ask, well, what is Smith's marginal rate of substitution between oranges and apples at point C? To answer that question, we're going to draw a tangent line through point C and his indifference curve there, a line that's tangent to his indifference curve at point C, and we're going to calculate the slope of that line. So the slope of this at that point C is going to be equal to the marginal rate of substitution for Smith at point C. MRS Smith at point C. That's actually going to be the negative of that, okay? And that's what the marginal rate of substitution is going to be. If we were at point F and asked what's Smith's marginal rate of substitution there, well, we would have to draw the indifference curve through F, and then we would have to draw the tangent line through F, and then we would calculate the slope of that particular line at point F, and we would get Smith's marginal rate of substitution at point F. Don't worry, you're not going to have to do that. We will not be asking you to derive the slope of a curved line at a point like C, because to ask you to do that would require calculus. Calculus is not required in this particular course. So I'm showing you how we would depict it, but I'm not expecting you to be able to actually calculate these values at a particular point, okay? Now, we need the marginal rates of substitution for Smith to be equal to the marginal rate of substitution for Jones at a point in order for Pareto optimum condition to be satisfied, for us to be at a Pareto optimal point. And here, down here in the corner, is what it's got to look like. So all of the indifference curves between Smith and Jones arranged in an Edgeworth box, again, where Smith is right side up, Jones is upside down, all of the tangencies of their indifference curves are going to be the set of Pareto optimal points that exist in the Edgeworth box. So let's take a look at that. Now you'll notice here, all of these points are, the green line corresponds to all of the Pareto optimal points that satisfy that condition, marginal rates of substitution equal to each other for the two agents. But this is the green line that's drawn only within the lens that represents the mutually advantageous trades. So that Smith and Jones care about increasing their utility, then we know they're going to trade into the lens somewhere. But if we imagine they're rational, we're going to imagine what's further true, that they're going to trade to a point that's on the green line, because the green line is going to be the only collection of points that will eliminate further gains from trade to be made. Let me give you an example. If they traded from point E down here on the far right up to this point here, call it point E now, a little different from the previous D, but similar. If they move from point E to D, then here the indifference curves cross each other between the two agents. And because they cross each other, there is a lens formed in here where they could trade further and raise up both of their utilities even more. So we wouldn't think they'd get stuck at a point like D, or a point here, or a point here, or a point here, or here. All of those points are ruled out because there's possibilities for further trades that could make both of them better off. But if they trade to a point like this, or this, or this, anywhere along the green line, well, now they can't go any further. They can't trade further and improve their well-being. So we call those points Pareto optimal. One last point I want to make. The green line represents the Pareto optimal points, again, in the lens, the ones that are mutually beneficial. But the Pareto optimal points actually extend. Pareto optimal line actually extends to the corners. We can continue with Jones's indifference curves and Smith's indifference curves like this, and we could find that there's more points where these two are tangent to each other. And they're going to extend, again, all the way to the corners. So in actuality, the Pareto optimal points formed along the diagonal. It doesn't have to be a straight line, though, because a straight line would only be true if indifference curves happen to be of a particular character. But they don't have to be. They can change their shape a little bit. They can have some oddities to it. And they're going to just kind of curve their way, this Pareto optimal line, from one diagonal to the other. And that's going to be the set of all of the Pareto optimal outcomes. Now, we would not ever imagine that they would point, because we know at that point, it's on a lower indifference curve for Smith. He would be made worse off. He'd have no incentive, even if he were just concerned about his utility, to trade to point N. So that trade wouldn't occur. But they could trade to the green point again within the lens and satisfy the rationality assumption. All right, now I want to emphasize something else, because we're going to use this terminology. Economists use this all the time, and I want to make the comparison, the equivalencies here of terms. If trade achieves a Pareto optimal outcome, economists say the outcome is economically efficient. And these two are generally equivalent for economists. Economic efficiency means achieving Pareto optimality, that all of the gains from trade or all of the improvements in the economic conditions have been realized when you reach a Pareto optimal outcome. And that is what economists are referring to as economic efficiency. And we're going to use that term, economic efficiency, throughout the course. Here's our first introduction to that term. Okay, so thus, economic efficiency means that there's no way to further increase the well-being of the individual traders. Now, in the pure exchange model, there's no increase in overall goods available. What do I mean by that? When they trade from the corner to the middle, they're not changing the amount of oranges and apples that are in this simple economy. Before and after trade, there are 10 apples and 10 oranges. they're only trading the allocation of the apples and oranges. So they're only mixing up who gets what. And despite the fact that there's no increase in overall goods, that mixing up of the allocation moving into the lens is actually increasing overall utility. Now, economists will also say that's increasing economic efficiency, but there's a type of efficiency we're describing here, and the type is called consumption efficiency. All right, now the last thing I want to highlight is an allocation can be very unequal and still be economically efficient. Let me go back to this diagram and remind you what I said is that this corner point, for example, up here, let's call it point W. At point W, Pareto optimality is achieved. Okay, at point W, Smith has everything. He has all of the apples and all of the oranges. Jones has nothing. But we would still say in economic terms that that particular allocation is economically efficient because there's no way Smith and Jones can trade from that point and make both of them better off. So it satisfies the conditions of Pareto optimality or economic efficiency, but it does not equalize the returns to the individuals. All right? And that's going to be an important consideration a little bit later on as we talk about economic inequality and the extent to which that's bad or good. In some sense, the economic model would be indifferent to that. It would say if we're trying to achieve economic efficiency, we have nothing to say really about what that implies about inequality or equality of outcomes for the individual traders. We can still be efficient and yet be very unequal in a particular society or economy. Okay, last thing, maximize utility. How do we get to a specific point on this diagram? How do we get to just one point in that Pareto optimal set that are mutually beneficial for the two individuals? Well, one way to get there is to impose the utility maximization assumption. If we do the exercise mathematically and use calculus to calculate things, what we find is that if Smith or Jones are given a terms of trade from the other and then asked to maximize their utility subject to that terms of trade, then we can identify what points they would want to trade to for every possible terms of trade that might be offered to them. We could then kind of find the intersection of those individual points and find, which one point would be satisfying those conditions simultaneously for the two. And if we did that, we would end up more than likely finding a unique particular point that they would want to trade to that would satisfy that particular condition. Now, the condition mathematically for maximizing utility is given here. Okay, and it's PO over PA is equal to MU over MUA. But these are terms we've already defined in the previous slides. In particular, PO over PA is a terms of trade and moving from the endowment to the point to which they trade. And MU over MUA, MUO over MUA is the marginal rate of substitution for an agent like Smith. So what we're saying is that in order to satisfy the maximization of utility condition for Smith, he's going to match the terms of trade that's being offered by Jones with his marginal rate of substitution at the point to which they trade. And he's only going to be willing to trade if those two are equal to each other. And likewise, if Jones is doing the same thing, look at down here, he's trying to find exactly the same condition. He's trying to match his marginal rate of substitution, the slope of his indifference curve, with the terms of trade that's being offered by Smith. And only when they're simultaneously true down below, where the terms of trade are equal to the marginal rates of substitution for both of them, only then are we satisfying the utility maximization condition for both. All right, here's what it looks like. And again, not going to be asking you to derive all of these things. You might be asked to derive a terms of trade because I've given you a method for doing that. But I haven't given you a method for deriving a marginal rate of substitution by finding the slope of a tangency to an indifference curve. That requires a lot more mathematics than we're going to use in this course. So instead, I just want you to recognize the depiction of an equilibrium that satisfies the condition. And this diagram is it. The endowment is down here at point E. They're trading, we're imagining, to a point like S. The terms of trade, TOT, between point E and S, is going to be given by the slope of the black line. I can't figure it out exactly, but it's going to be about 4.5 apples divided by 5.5 oranges or so. I won't even try to do that, but that's going to be the ratio of those, rise over run, the slope of that line is going to be the terms of trade. The marginal rate of substitution for Smith is going to correspond to the slope of the red indifference curve that passes through point A. And the slope of that indifference curve, point S, is going to be equal to the slope of the black line, which happens to be the terms of trade. And likewise, the marginal rate of substitution for Jones is going to be equal to the slope of his blue indifference curve, at point S, which is also equivalent to the slope of the black line. So this point S satisfies, and so therefore we would imagine they move to a point like that. Now let me give you a counterexample of a point that's Pareto optimal, but not utility maximizing. And that would be a point like O right here. Suppose they traded. The terms of trade between E and O is equal to, well, we could calculate it explicitly. It's going to be equal to 1, 2, 3, 4, 5, 6, 7 apples divided by 3 oranges. 7 divided by 3. So that's going to be the terms of trade between E and O. And it's going to correspond to the slope of that straight line. But if we were to ask, what is the marginal rate of substitution of Smith at point O? Well, I can't calculate it, but I can see it visually. Actually, let me change it from Smith to Jones because I can see that easier. At Jones's, his marginal rate of substitution at point O is going to be given by the slope of the line that's just tangent to his indifference curve at point O. So the slope of this, negative of the slope, is going to be equal to the marginal rate of substitution for Jones. But it's also equal to the marginal rate of substitution for Smith because this is a Pareto optimal point and Smith's indifference curve is also like this. Sorry, messy looking, but notice that the marginal rates of substitution here are equal to each other. Marginal rate of substitution of Smith at O is equal to the marginal rate of substitution Jones at O, but it is not equal to the terms of trade. And therefore, the utility maximizing condition isn't satisfied there. It's unlikely to be satisfied here either, or here only at S. It's quite likely, given mathematical regularities of the function, that we can achieve a unique outcome with these particular conditions. All right? And that's now satisfying to economists in a sense, because if we want to work with this and we want to say, okay, suppose there's some changes in conditions in one way or another, if we're stuck saying, well, we only know they're going to trade somewhere into this lens, but we don't know where, and now we change something and we say they're still going to trade into the new lens, but we don't know where, then lots of different outcomes might be possible. But if we can narrow it down to a particular outcome, we have more seeming predictive power about what's going to happen. And then we can actually use the model more effectively to think about changes that might then affect that particular equilibrium, right? So in terms of going forward with analysis, these conditions become important in order to work with and use the models. Now, last slide. I want to emphasize this. If Smith and Jones are merely utility seeking, if that's the extent of the assumption we make about their behavior, they just care to get to an increase in utility, they don't really care how much, and they're not really using all of the information possible, then all we need to do is to say they're going to trade to some point in the lens of the Edgeworth box. That's EB. EB is Edgeworth box. And they're both going to become better off from trade. So that becomes the implication of that particular assumption. And that's an important outcome because, this model is not meant to be a model that only describes trade between individuals in the world named Smith and individuals in the world named Jones. It's not meant to represent a world in which two individuals can only trade apples for oranges. It's meant to represent any individuals, by whatever name, who might trade any two things with anyone else in a mutually voluntary way with good information. And what this model then tells us is that if individuals are motivated by self-interest, that they're actually, through trade, it's possible for them to both increase their own self-interest and well-being, while simultaneously increasing the interest and well-being of the other trader as well. And that is an important outcome that may well be indicative of many or most of the trades that actually take place in the world every day. Now, we're going to think about that a little bit more carefully next time in class. But it's opening up the possibility of this notion that Adam Smith had, that if individuals pursue their self-interest, it can actually lead to the benefit of all, or at least to the benefit of everybody they're trading with. That self-interest motivation and realization of that self-interest through trade can actually be, not will be, can be a mutually beneficial outcome. Now, last point here, if Smith and Jones are rational and utility maximizing, then those additional conditions that we described at the end are going to come into play, and we're going to imagine they will trade not just to any point in the lens, but to a Pareto optimal point that also satisfies the utility maximizing condition. And still, both of them become better off from trade. So we don't get a change in that broader outcome that people gain from trade by pursuing their self-interest, but we get a more precise outcome by introducing the rationality and the utility maximizing assumptions.